Hello, we're excited to show you our final project for microcontrollers, that being a digital guitar effects pedal and amplifier.
We'll quickly introduce ourselves. I'm Phillip Dustin, and I'm a junior studying electrical engineering.
I'm Andrew Romanovsky, and I am a junior studying electrical engineering.
And I'm Blake Giles, and I'm a junior studying electrical engineering. I would like to show you now the inner workings of our project. So, as you can see, we've built this box for it. We have all of our peripherals on the front, our speakers, the buttons, the LEDs, and the LCD. But we made this so it's able to be portable. This top opens up and we can see what's on the inside. So currently we have the power running to the microcontroller sourced from this battery pack. Additionally, we have these two 9-volt batteries that supply the plus or minus 9-volt power rails for our op amp within there. And then of course we have the audio signal that comes from this cable. So now we're going to look at the circuits themselves. So I'd like to draw your attention first to here. This right here is our preamp circuit. Right here is the TL084 op amp chip. What's really neat about this chip is it has low noise, which means it's good for audio applications. Additionally, it has 4 individual op amps on the inside. Furthermore, we've got some capacitors, resistors, and our potentiometer right here that help to produce the correct gain and to limit noise. Now if we come right here, this is our amplifier coming out of the DAC. This set of capacitors and resistor right here is our reconstruction filter and DC blocking filter. This potentiometer right here is our volume control. And this chip right here is the PAM8403. This is a pre-built amplifier that is well used for small audio applications like this. We're able to run it off of 5 volts, and we're able to source power into these low impedance speakers. So the buttons are down here below. They're kind of hard to see, but then we have our LCD right here and our LED right here on the top.
Here is the block diagram for our proposed design. First, the signal gets sent from the guitar to the preamp, which prepares the signal for modification by the microcontroller. On the microcontroller's end, the signal gets sent to an analog to digital converter, which converts the signal to a digital signal. Next, the STM32 microcontroller uses digital signal processing to implement 5 different guitar effects. These guitar effects can be selected by buttons that are on the front of the housing. There is also an LCD on the housing that displays the current effect being used. After the effect is applied, the signal is sent to a digital to analog converter. The amplifier is used to increase the strength of the signal and to allow the speakers to produce an audio output.
This is the circuit diagram that we've come up with for our preamp design. The main reason we need a preamp is because of this guitar input signal right here. It is unprepared for audio processing at this moment. So what the preamp does is it prepares it to be processed by the ADC. The way it does this is it removes the high impedance using an op amp system. It also applies a gain to bring it back to the level it needs to be. Because at the moment, the input is at about 200 millivolts peak to peak, and we needed a lot higher than that to make use of the entire functionality of the ADC. Another part that we had to worry about is that the ADC over here can only accept values between 0 and 3.3 volts, whereas the guitar inputs will dip down to the negative voltage range. So this system right here involves something called a voltage injector. And this voltage injector takes this 3.3 volts supplied from the microcontroller, does a voltage divider to find the midpoints of it, does some filtering, and then injects it right here to make a DC offset that is our new midline for the ADC conversion. The rest of this circuit up here is the preamp. We're able to control the gain using this potentiometer. We're able to filter out some noise and block DC flowing back into it using this capacitor. And essentially what it does is it'll apply that gain we need to bring it up from 200 millivolts to a usable range. And then it sets the midpoint to 1.65 volts. So it is able to be processed by the ADC and prepared for digital signal processing. Now we're going to talk about the effects that we use in our DSP, or digital signal processing. So for our design, we wanted to incorporate 5 different effects that could apply to the guitar signal. So the first effect we had is just bypass. this is the simplest one to implement because it just takes the input from the ADC, brings it straight to the DAC. And there's no effects happening at all to it. There's no digital signal processing. All it is just a pass through. So this is what we'd want to do if we wanted a clean, unaffected guitar signal. The next one we implemented was distortion. And distortion was actually pretty simple to implement because all it involves is applying a threshold to the signal and ensuring that if it goes above it, it'll be brought back down to the threshold. If it goes below it, it'll be brought back up to the threshold. This essentially clips the signal and produces a distorted sound. The next one we implemented was something called an echo. And this one was a little more complicated. So essentially, it takes in the previous inputs, adds it to the current input, and the sum of them are brought to the DAC. Next, we have tremolo. And tremolo is an effect that varies the volume of the signal coming through. So what it makes use of is something called an LFO, or a low frequency oscillator, that provides just an up and down sort of signal that at pretty low frequencies. And what this does is we're able to modulate the signal to adjust the amplitudes depending on the time. So it's the same signal, but the only thing that's changing is the volume or the amplitude of it that produces just a varying volume as we play the signal through. And finally, we have the flanger. The flanger is the most complicated out of all of these because it involves a low frequency oscillator as well as the echo effect. It takes this low frequency oscillator we used for the tremolo and applies it to this buffer method that we have here with the echo. So it has an echo, but a much shorter delay than for the normal echo effect, and it applies a low frequency oscillation to it. So it sounds like a whooshing sort of sound as it goes through.
So this is the audio output circuit, and it starts with the output from the DAC, which is a discrete signal, and it's very choppy. So the reconstruction filter smooths out the transition between discrete values. The signal also has a DC component, which leads to a 1.65 volt offset, and that is removed with this capacitor. The signal then goes through a potentiometer, which allows the volume to be adjusted. After the potentiometer, the signal then goes to an amplifier, which amplifies the signal and allows it to drive speakers and produce an audio output.
For our project, we're using a strip of individually addressable LEDs, like this one. The strip takes in 5 volts of power, as well as a single data in line. This line carries a digital signal that can control all the LEDs on the strip. This is possible because each package has an integrated circuit that understands the signal and then sets the red, green, and blue to the right amounts. You can use these amounts to represent any color or shade that you want to. So for example, this shade of orange can be represented using a green part, a red part, and a blue part. So the question is, how do we send this color code to all the LEDs? Well, first we represent it in its binary form, and then according to the data sheet, we can send a 0 by sending a short pulse, and we can send a 1 by sending a long pulse. The frequency of this digital signal is 800 kilohertz. So we use DMA in conjunction with the microcontroller timer to create such a rapidly modulating square wave. The timer 2, whenever it expires, sends a request to the DMA, which fills it with a new CCR value, such as the number 6 here for 0. And once it's generated that pulse, it'll request the DMA again. So we put in a 13, which helps us generate the long pulse. This way, we can generate the series of pulses from a buffer at a really rapid rate so the LEDs can understand and turn the right color.
In conclusion, we were able to successfully implement a digital guitar effects pedal and amplifier using the microcontroller. Our first goal that we achieved was to have a preamp circuit that would convert the audio signal from the guitar to allow it to be used on the microcontroller. Our second goal was to use digital signal processing to have multiple guitar special effects on the microcontroller. Our third goal that we achieved was to have a sound being produced by the outputs of the microcontroller. Our fourth goal that we achieved was to use multiple buttons to select which guitar effect was being used. Our fifth goal that we implemented was to use an LCD to display the current special effect being used. We also had a sixth goal of using an LED strip to display the waveform of the audio signal. However, this was never implemented due to time constraints.